Hi, in this video I'm going to go over epoxides, both the formation of them and then the typical reactions that they'll undergo. So epoxides are a special type of ether, and they are three-membered cyclic ethers. This makes them more reactive than the typical ether that we've studied. Now, these ethers can be either unsubstituted, substituted at one position, substituted at both positions. So I could have, the simplest of ethers here with just two hydrogens on each of the carbons. I could have, substitutions at one of the sites, or I could have an ether that is substituted at both of the sites. Now, there's a couple ways that we can form these ethers, and they're going to be similar reactions to the different alkene reactions that we studied earlier to produce them. So one is going to be using peroxy acids. So for example, if I have that alkene, the most common peroxy acid that will be used as a reagent for these is going to be MCPBA. And that's a reactant that we studied earlier in one of the videos. And this peroxy acid will reduce the alkene and form the epoxide. So we'll get our epoxide. And notice here that the two methyl groups, well, you'll have the enantiomer too, and the two methyl groups are trans to each other, just like the two substitutions here are trans to each other. So the stereochemistry is going to carry over. If I have a cis and react with MCPBA, I'll get cis substituted epoxide. Right, so the stereochemistry carries over for the peroxy acids. And the stereochemistry will carry over for the other reaction that's common to forming epoxides, and that is reactions with halohydrins. Right, in this reaction, I've got an alkene reacting it with bromine and water, and I end up getting not initially an epoxide. I get an alcohol and a bromide. And notice they're trans to each other because of how the halohydrin formation works. Remember, the bromine will form a bromonium ion, and then the water will come in and attack underneath or on the opposite side, and that means they're going to be these two enantiomers. So what I can do now that I have this product is I'm going to draw here in the chair conformation to make it a little bit easier to see. So I've got my OH group up here and my bromine group down here. And I'll draw the oxygen-hydrogen bond because we'll have a deprotonation. So if I use a strong base like NaOH, so I've got my hydroxide ion, I'll come in and deprotonate the hydrogen. And now you'll end up with the deprotonated oxygen and the negative charge. The electrons from this oxygen can now come down here and kick off the bromine. And you'll end up with your epoxide now. So that's it in the chair structure, right? This would be equivalent to And notice I'm not indicating the wedges or the dashes because the carbons are not chirality centers here, because it's symmetric. So that's the other way you can form the epoxides. And like with the peroxy acids, again, it will maintain the stereochemistry that you had. So if you had a trans substitution, you'll still have a trans substitution. If you had a cis substitution on the alkene, it'll remain a cis substitution after you form the epoxide. Now, once you've formed these epoxides, what type of reactions are they going to undergo? Well, the major one, or class of them, you could say, is going to be the ring opening reactions. These are so common because when you have such a tiny ring, like an epoxide, with just 2 carbons and an oxygen, those atoms are closer together than they'd like to be. Right? The bond angle is smaller. So, they will undergo reactions that will allow them to open up that ring and relieve the small bond angles and the steric interactions you'll have between the atoms. So the first one is going to be reaction with strong nucleophiles. So if you have a strong nucleophile present, say NaOH, I'm going to number my carbons here, 1, 2, and 3. The OH minus will come in and attack at carbon 3, and those electrons will travel up to the oxygen. The reason it attacks carbon 3 is it's the less substituted position. So just like with SN2 reactions, where it'll favor attacking the less substituted position, it's the same thing here because it basically is an SN2 mechanism. So it'll attack the less substituted position. I'll end up with now a deprotonated oxygen. Then this is carbon 2 and 1. We have carbon 3 right there, which is now bonded to an alcohol. Now you would just add in, water to the solution to protonate that oxygen, and you'll end up with your product. Now notice here, the stereochemistry of the methyl group didn't change because it wasn't at the site of attack. But had the methyl group been at the site of attack, you would have inversion of stereochemistry, right? Because it's an SN2 mechanism, right? So consistent with all SN2 mechanisms, you have inversion of stereochemistry. Now, Grignards are often used as these strong nucleophiles, right? So if I have another reaction here, just with the simple epoxide, number my carbons 1 and 2, and I react here first with my Grignard. So in this case, bromo, magnesium, propane. And then I add in the water to protonate. I can attack either carbon 1 or 2. They're identical, so it doesn't matter which one. I can't even differentiate between the two of them. I'll end up with the alcohol. That's carbon 1 and 2. Right, that's carbon 3, 4, and 5. So 2, 3, 4, and 5. And I'm being very careful here to number the carbons because with these epoxide reactions, because there's only 2 carbons on the ring and often you're adding carbons in, especially if it's a Grignard reagent, you can lose track of the carbons a little bit. So you want to make sure to always number, one, so that you have the correct amount, but also to make sure you're forming bonds between the correct carbons. Here I'm attacking carbon 2, so I should have a bond between carbons 2 and 3, which I do. So the second type of ring opening that epoxides will undergo is acid catalyzed. And here I'll use the same substrate I used for the first example of the previous ring opening that we did with the strong nucleophiles. The acid catalyzed is honestly very similar to what you'll get with the strong nucleophiles, because first you protonate with a strong acid, and now the conjugate base of that strong acid is a great nucleophile, and it comes in and attacks at the less substituted position. And you end up with your product. Again, only one stereo center here, right? No stereo center at the other carbon, so that's our only stereo center. And it remained the same. It didn't change. Now, one thing to note with the acid catalyzed is not only do you have to consider the steric effects, which is why here you attack the primary over the secondary, but there's also electronic effects to consider. So a tertiary substituted carbon is more electrophilic than either primary or secondary. So, primary is favored over secondary, and as was shown in this last example, right, it attacked the primary site because of the fewer steric interactions undergoing at the primary site. However, once you get to tertiary, the electronic effects trump the steric effects. So tertiary is favored over primary. So now, if I have that as my epoxide, and I react with the same reagent, I'll protonate, but then the Cl- will come in and attack the more substituted site. And I'll end up with that as my product. So that's something to keep in mind. If it's acid catalyzed ring opening and it's a tertiary site versus a primary site, it'll attack the tertiary site. If it's tertiary versus secondary, it'll attack tertiary. And if it's secondary versus primary, it'll attack the primary. Now, last thing to note is that you can also have the acid catalyzed ring opening if you first use a non-nucleophilic strong acid, so one that's conjugate base isn't a nucleophile. So, for example, H2SO4. Right, strong acid, but its conjugate base is not a nucleophile. So I protonate, draw it a little lower so I can fit it in. So I protonate. Now you can react it with an alcohol. So say ethanol. Ethanol can come in and then you just have to deprotonate to get your final product. And I formed another ether when I react with the alcohol. You can also react with water rather than alcohol, and that will just form a glycol. So you'll have two alcohol groups. So you can do that if you use a strong acid whose conjugate base is not a nucleophile. So basically not HCl, not HBr, not HI. You could use HNO3, right? That's another one that would protonate the epoxide without having the conjugate base then come in and act as the nucleophile.